Hello everybody and welcome back to Algebra 2. Today we're going to be talking about 5.5 theorems about roots of a polynomial equation. Let's begin. Let's start off with a little vocab and review. Write L if the polynomial is linear, Q if it's quadratic, and C if it's cubic. Well, in order for something to be linear, that means that it has to have a degree of 1, also known as an x raised to the first power, which we always write as x. A quadratic is going to be a degree of 2, so it's going to be x squared, which is what we always can see as x squared. And then the degree of 3 will be that cubic, meaning that we're looking for anything that has the highest exponent being a 3. So taking a look at the very first one, although we do have the x to the first power, we also have the x squared, and therefore the degree of this is 2, making the very first part quadratic. The highest exponent that we are given in the second part is the 3, making it cubic. And last but not least, since we have an x by itself, that's really x to the first power, which is linear. So let's talk about what is a root. Other related words could be things like a factor, a solution, a zero, or an x-intercept. But the definition is a root of an equation is the value that, when substituted for the unknown quantity, satisfies the equation. And the main idea of this is essentially, well, a root is going to be the solution. It's also going to be considered the zero or the x-intercept because it's where it crosses the x-axis. However, you can also consider it the factor in a weird way. The only difference is, when you start talking about it as a factor, it's going to be the opposite of whatever that known number or known root ends up being. So in this case, as you can see, it says if x minus a is the factor of the polynomial, then a is the root of the polynomial. However, that negative means we're going to be talking about its opposite. So essentially, solve it, and we can find the roots. So looking at the very first question, question number 2, we have 1 and negative 1 are roots of the equation x squared equals 1. Well, if I were to solve out x squared equals 1, I would take the square root of both sides. You get x is going to equal a plus or minus the square root of 1 is in fact 1, and therefore the solutions will be plus or minus 1, making the roots plus or minus 1. The equation x squared minus 4x plus 4 equals 0 has the roots 4 and negative 4. Well, in this case, if we were to factor this one out, you'll get that we have an x minus 2 and an x minus 2 in order for us to actually get this. So our factors are negative 2 and negative 2, meaning our root for this problem is actually going to be 2 with a multiplicity of 2. So in this case, for question 3, that's going to be false. Write the number of roots each polynomial has. Now, when we're talking about the number of roots, we just have to pay attention to the degree, or the highest exponent. Whatever the highest exponent tends to be is how many potential roots there will be. Alright, so in this case, we have the highest degree of 4, so the number of roots will be 4. The highest degree that we get is not going to be this 5, although it is in the front. It's actually going to be the 7, and therefore there are 7 roots. And the final one is the x to the first power, because x by itself is that, and therefore it's going to be only 1 root. Great job. Problem 2. Using the rational root theorem. What are the rational roots of 2x to the third plus x squared minus 7x minus 6 equals 0? Underline the correct number or numbers to complete each sentence. Well, the leading coefficient is going to be 2, because the 2 is attached to the highest exponent degree, which ends up being 3. So we're going to end up underlining the 2 because that's our leading coefficient. The constant, or the number that's by itself, is going to be a negative 6. Paying attention to that sign is very key. The factors of the leading coefficient, or the factors of 2, will be all of the numbers between 1 and 2. So we have a 1 and negative 1, a 2 and a negative 2. Remember, we need to have the positive and the negative versions as well. The factors of the constant are going to be the 1, the 2, the 3, and the 6, because 1 and 6 and 2 and 3 will both multiply to that 6, but more importantly, we need to make sure we also have their negative counterparts. So we have the positive and negative 1, positive negative 2, plus or minus 3, and the plus or minus 6. Cross out the numbers that are not possible rational roots. Well, if it's not underlined, we can't have it, so that 0 is gone. Negative 1, well, we have a 1 divided by a negative 1, or we could do a negative 1 divided by 1, regardless of the fact that is a possible rational root. What we can't have, however, is the constant, because remember, it is going to be the constant over the leading coefficient factor. So we'd have the constant over the leading coefficient. And since we have it like this, our 1 would have to be divided by this 3. In this case, it's not underlined, so we can actually cross that one out. And last but not least, we have the 1 divided by 2, or the negative 1 divided by negative 2, both of which are good, so 1/2 is possible. Now, the rational root theorem is here for us to be able to basically do what we just did, and that is eliminate possible roots that we don't want to have to worry about solving out, especially if they're not true. But it also leaves us with easier possible roots to work with. So you must always try the easiest possible root. In this case, that would be like using 1 or negative 1. Those always tend to be the first easiest, usually trying to stay away from fractions from here and there. So we can do one of two things. Either A, plug the 1 into every single one of these x values. So you get something like a 2 times a 1 cubed plus a 1 squared minus a 7 times a 1 minus 6. And we are going to figure out if that does in fact equal 0. Well, plugging it in, you're going to find out really quickly that that's going to end up equaling a negative 10. And since that's a negative 10, we know that this is not a possible root. So we are going to try that negative 1, only in this case, I'm going to try it using the synthetic division way. Since we have a piece of negative 1, I'm just going to put the negative 1 up in the top left corner. I'm going to underline everything, and I'm going to have a remainder reminder at the very end. Now I'm going to put all of the constants. Now I'm going to put all of the coefficients in. So we have the 2, the 1, the negative 7, and last but not least that negative 6, making sure they're not skipping over any terms, and they aren't. We started with a 3, we went down to a 2 for the exponents, then a 1, and then a 0, so we're good. And then let's just synthetically divide. So we have a 2. 2 times negative 1 is negative 2, which gives us a negative 1, which gives us a positive 1, which gives us a positive, which will give us a negative 6, and then we get the positive 6 right here, leaving us with 0. Therefore, piece of negative 1 equals 0, and it is in fact a factor. So let's kind of continue on through that portion. Since negative 1 is in fact a factor, or it is a root, we now can figure out the factor. Well, the opposite of the root is going to be the factor. So if it's a negative 1, therefore the x plus 1 is going to be the factor of this equation. And we kind of already did the synthetic division, but let's kind of break it down once more. Going through it each and every step of the way, we get that 0. And then remember, this last little bit is that remainder reminder. So the quotient is going to be a 2x squared minus x minus 6. The 2 goes in front of the x squared because we're taking 1 away from that degree. The negative 1x comes from that negative 1, and that minus 6 is going to be that constant. The other way you can think about it is the number next to the remainder is always a constant, and then you can start counting up when it comes down to the degrees. So the 0 goes to the 1x, or goes to the x to the first power, which then goes to the x to the second power. All right. Using our quadratic formula, we can find the remaining roots. So we're just going to start plugging everything in. Well, our a value is 2, our b value is negative 1, and our c value is negative 6. So we are going to put a negative 1 right there, which originally is a negative times a negative 1, which is why we have a positive 1 right there. We then have a positive 1 because this is a negative 1 squared minus a 4 times our 2 times our negative 6 all over 2 times 2, which is 4. And if we were going to simplify that down a little bit more, we have a 1 plus or minus, and we have a 1 minus, in this case, it's going to be a negative 4 times 2, which is 8, times 6, which is a negative 48, we can notice that it is eventually going to be a plus, but it's again divided by 4. Right? The square root of 1 plus 48 is the square root of 49. It's going to end up being 7. So we have 1 plus or minus 7 divided by 4, or we have 1 plus 7, which is going to be the 8 over 4. And then we also have a 1 minus 7, which is going to be a negative 6 over 4. So if we were to simplify that down, the 8 over 4 becomes the 2. Or we could have the negative 6 divided by 4, which is a negative 3 over 2. Therefore, the rational roots of 2x cubed plus x squared minus 7x minus 6 equals 0 are going to be a negative 1, a positive 2, and a negative 3 over 2. And when you look at it, another theorem, the conjugate root theorem. If p sub x is a polynomial with rational coefficients, then the irrational roots of p of x equals 0 occur in conjugate pairs. That is, if a plus the square root of b is irrational root with a and b rational, then a minus the square root of b is also a root. In other words, if p of x is a polynomial with real coefficients, then the complex roots of p of x will equal 0 and occur in conjugate pairs. That is, if a plus bi is a complex root with a and b real, then a minus bi is also a root. That's a fancy way of saying, hey, if one of our solutions happens to be something like 1 plus 3i, well then we also know that the conjugate of that root will also be a solution. So if 1 plus 3i is a solution, or a root, 1 minus 3i will also be a root. 4 minus the square root of 7 is a root. Well, same exact thing, 4 plus the square root of 7. Now, a lot of that you can kind of pay attention to the quadratic formula and the fact that we always have that b plus or minus the square root portion. That plus or minus is essentially what we're putting here, because remember, in order for us to get the I, it's the square root of a negative number. Well, if we don't have the square root of a negative number and we're using a square root symbol, or a root symbol, in this case, it's still going to be plus or minus. So we have a negative 2 minus the 9i is still going to become a negative 2, stays the same. The 9i will be changed to from a negative to a positive. And then we have a 15 plus the square root of 10, which means that the other root must be the 15 minus the square root of 10. Problem 3. Using the conjugate root theorem to identify the roots. Well, if a cubic polynomial p of x has real coefficients, if 3 minus 2i and 5 over 2 are two roots of p of x equals 0, what is one additional root? Well, place a check if the conjugate root theorem could be applied to the following types of roots. Place an X if it can't be. Well, if it's a rational root, then we know that it can't be. Alright, a rational root is a straight up answer. In this case, that 5 over 2 is considered a rational root, and therefore we can't worry about using this conjugate root theorem. However, irrational roots can work, and same thing with complex numbers. So write R if it's a rational, or I if it's irrational, or C if it's a complex number. In this case, 3 minus 2i is going to be complex. Why? Because it has an imaginary number attached to it. And like I said before, the 5 over 2 is going to be considered rational, which means that we know for a fact that that one cannot be done using the conjugate root theorem. And therefore, by the conjugate root theorem, we're going to pay attention to the complex number. We would have a 3 minus 2i. The complex conjugate in this case would end up being a 3 plus 2i. That is going to be our additional root. Problem 4. Using conjugates to construct a polynomial. What is a quartic polynomial function with rational coefficients for the roots 2 minus 3i, 8, and 2? Underline the correct word or number to complete each sentence. A quartic polynomial has 4 roots, because that's the x to the 4th power. Since 2 minus 3i is a root, 2 plus 3i is also going to be root because of the conjugate theorem. Write p of x as a product of 4 binomials. Well, remember, our factor is our x value minus whatever our a value is, and our a is going to be considered our root. So essentially, it's just going to be x minus whatever our root is. So we have x minus a 2 minus 3i. We have an x minus an 8, an x minus 2, and finally we'll have our last root, which is that x minus a, in parentheses, 2 plus 3i. And if you were to go through and multiply out each and every one of these, paying attention to the i's, and everything will drop out, but you're going to find out that the i's will actually cancel out completely, and you're going to be left with 100% rational coefficients, which will give us the end answer, which isn't going to be the bottom portion because that is not a quartic. So if you were to multiply everything out 100%, you're going to end with x to the 4th minus 14x cubed plus 69x squared minus 194x plus 208. And let's talk about the last theorem of this lesson, Descartes' rule of signs. Let p of x be a polynomial with real coefficients written in standard form. The number of positive real roots of p of x, or the polynomial, is either equal to the number of sign changes, so essentially going from a positive to a negative, between consecutive coefficients, or it's going to end up being less than that by an even number. So say we have something like a positive minus, or positive and another minus. That's going to give us 1. We have 2. And then 3 total changes. That means that we are either going to have potentially 3 possible positive real roots, or the even number under that 3, which is going to be 1, 2, making it that 1. So it's going to be 3 or 1. All right? And doing the exact same thing for the negative roots, the only difference is we aren't going to base it off of the original polynomial function. We're going to actually plug in a negative x for all of these x values to be able to figure out whether or not this is going to have a certain amount of negative roots. Again, negative real roots. All right? But we're also still following that whole less than by an even number as well. Alright, so a possible number of positive real roots for x to the 4th minus x to the 3rd plus x squared minus x plus 1 is going to either be 1, 2, 3, or 5. Which one is it? Well, we're starting with a positive, then going to a negative. So that right there is a jump of 1. We have a negative to a positive, which is 2. Positive to a negative, which is 3. And last but not least, we have a negative to a positive, which is 4. So, the possible positive real roots is going to be either 4, or since we can be an even number under 4, we're going to be going down 2 from 4, which gives us a possible 2. So in this case, 2 is that correct answer. So let's jump into problem number 5, knowing that Descartes' rule of signs. What does Descartes' rule of signs tell you about the real roots of 2x to the 4th minus x to the 3rd plus 3x squared minus 1 equals 0? Well, the number of sign changes is 3 because it goes from positive to a negative, which is 1, negative to a positive, which is 2, and last but not least, positive to a negative, which is 3. And therefore, we're either going to have 3 or 1 possible real positive solutions or roots. Knowing that, we're going to change up all of the x values. We're going to plug in the negative x into wherever we see an x. So we're going to have 2 times negative x to the 4th, a negative times a negative x to the 3rd, plus a 3 times a negative x squared minus 1. If we were to solve out each and every one of these, you're going to end up getting a 2x to the 4th plus, because this is going to end up being a negative x to the 3rd with a double negative right here, making a positive x to the 3rd, plus a 3x squared minus 1, which equals 0. Therefore, the number of sign changes for this problem is actually going to only happen once, because we're starting positive, keeping positive, then we finally change it to that negative, meaning that there is going to be one possible real negative solution to this problem, and the number of negative roots has to be possibly 1. And we made it, guys, to the lesson check. Let's get through this real quick. So, in the statement below, R and S represent integers. Is the statement sometimes, always, or never true? And can you explain? Well, a root of the equation 3x to the third plus rx squared plus sx plus 8 equals 0 could be 5. Well, let's write the factors of 8. In order for us to write the factors of 8, we have to make sure we get all of them. So it's going to be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. The next one is we have to write the factors of 3, which is plus or minus 1 and plus or minus 3. Because there are no factors of 5, the statement is never going to be true. So once again, really quick, we cannot basically take the factors of the constant and divide it by the factors of the leading coefficient and ever eventually get a 5, and therefore that 5 cannot be a factor or a root or a solution of this problem, and that's why it's considered never true. I hope everyone has a wonderful day, stay out of trouble, don't do anything stupid, and I'll be seeing you guys in the next one.